In this work, learning spectral unions of partial deformable 3D shapes, we explore the properties of the Laplace-Beltrami spectra. The Laplace-Beltrami operator generalizes the classical Laplacian to surfaces and can be used in the same way to perform Fourier analysis on surface signals. This is done by computing its eigenvector and eigenvalues. They have interesting properties. For example, the slope of the eigenvalues is proportional to the shape area. Meanwhile, the specific values depend to the shape geometry. It is common knowledge that the Laplacian eigenvalues encode geometry information. Indeed, recently, there have been attempts to recover the shape from the Laplacian eigenvalues. However, no one ever did set operation between eigenvalues. Usually, the Laplacian is used to analyze properties and relationships between shapes. In this work, we show that the spectra can be used to perform set operations between different shapes. This is the general overview of our work. We are given two partial shapes. In particular, we are given the spectra of those partial shapes, and we want to compute the union spectrum completely in the spectral space. And this union spectrum, here in green, represents the spectrum of an unknown shape that is the union of the input shapes. And once we have this spectrum, we can address several tasks. For example, we may want to localize the region of those partial shapes on a fixed template. So working in the spectral space presents several advantages. For example, to solve the previous task of region localization with a typical pipeline, we would need to first find the partial correspondences between the two partial shapes. Then we should extract a non-rigid transformation to transform one shape onto the other. And then we should merge the partial views into a consistent discretization. Each one of these steps is a challenging research problem. Instead, working in a spectral space, we are completely correspondence-free, and we sidestep those hard problems. Moreover, the Laplacian is invariant to isometries, and we are invariant to representations, as long as we can define a Laplacian Beltrami operator on that discretization. For example, we can handle triangular meshes or point cloud in the same way, because we only need the spectra of the Laplacian. So the architecture to perform the spectral union is the following. Given the two shapes, and in particular given their eigenvalues, we compute the union eigenvalues with a spectral union operator. That is a learning model, it's a narrow architecture. This is quite simple. Let's go through it step by step. The data that enters the learning model is sequential in nature. So we use learning models that know how to digest this type of data. In particular, we use two transformers that take sequences of eigenvalues as input. They are Siamese in the sense that they interact in a symmetrical way, sharing the weights. So they are basically the same transformer used twice in a symmetrical way. Those two transformers produce the embeddings of the two spectra. And those embeddings are summed together. The sum produces the embedding of the union spectra that is then decoded by yet another transformer. The output of this model is the spectrum of an unknown shape, which is the result of the union of the two input shapes. In other words, we are rephrasing the problem of the union shapes in making the sum of the embeddings of their eigenvalues. Then, during training, the loss is just the mean squared error between the approximation of the union eigenvalues against the ground truth eigenvalues. Once we are able to predict the union eigenvalues, we can address several tasks. For example, geometry reconstruction. recent work by Marine et al. It instant recovery of shape from spectrum via latent space connections is able to recover the shape from its eigenvalues. So given some numbers that are the eigenvalues of an unknown shape, this method is able to recover the shape that is represented by those eigenvalues. It only works with complete shapes. So we do the following. We extend this method to work on partial shapes by first approximating the union eigenvalues with our spectral union, and then feeding the approximation to the instant recovery pipeline. So in this example, we are given two shapes in red and green, M1 and M2. We compute the approximation of the eigenvalues of the union, and then we feed this approximation to the instant recovery pipeline. And this way, we are able to recover the extrinsic geometry represented by those spectra. Here it is interesting to note that the instant recovery pipeline does not work with partial shape. So if we feed the spectra of M2 to the instant recovery pipeline, the error is much higher, and it's shown in red, compared to first approximating the union of M1 and M2, and then feeding this union to the instant recovery. Again, this whole pipeline does not need any correspondence, so we are completely correspondence free. We do not know nor approximate or compute the correspondences between M1 and M2. The second task that we are going to address is the region localization. In this task, we are given two shapes, here in red and green, and the goal is to localize the region spanned by those partial shapes on a fixed template. Here, the region is localized in yellow. We are able to do that using a simple multi-layer perceptron that takes as input the approximated eigenvalues of the union and predicts a scalar function on the template. This scalar function takes values 1 if the region should be there, or 0 otherwise. Note how their discretization of the two partial shapes is not uniform. But this is not a problem, because we can always increase the order of the Laplacian discretization to improve its approximation. We also experimented on different classes of other than humans, here on horses. And this is particularly interesting because the spectral union operator has not been trained from scratch to work on horses. We just took the spectral union trained on humans and fine-tuned it to work on horses, and it worked very well. As you can see, the region localized is quite accurate, regardless of the discretization or the differences between the horses that are quite different. We also experimented on different representation. For example, here you can see that we are working with point clouds. So we are given two point clouds in red and green. We define and compute the Laplacian on those point clouds and compute their spectra. Then we perform the spectral union and then localize the region on a fixed template. Our method is a union operator, so of course it is associative. So we can perform the union between the first two shapes and then perform the union between the output of the first operation and a third shape, so that we are able to compute the union of three shapes. We also experimented on rigid objects. These are airplanes from the ShapeNet dataset. And as you can see, the eigenvalues are still quite accurate. Here you can see an interesting behavior where the two partial shapes in red and green are defined on the right wing of the airplane, but the region is localized on the left one. The region localized is correct, is semantically correct, but is on the wrong side. And this is because the Laplacian operator is invariant to isometries. So it's not able to distinguish between left and right. But nevertheless, this is a correct region localization. We also performed experiment on headphones. In particular here, the region localized contains many symmetries. So the spectra assumes an interesting behavior that we are able to correctly predict. And in general, the spectral prediction is quite accurate. Of course, when talking about associativity, if each time that we iterate the union operation over another approximation of the eigenvalues, we carry over the error. So in each union operation, we increase the error in the prediction. An interesting experiment that we did to showcase the generalization ability is the following. So we are given two shapes in green here, and we consider their spectra. We linearly interpolate the spectra of those two shapes to obtain k different shape spectra. Then we are given another shape in red here, and we consider its spectrum. And we compute the union between the spectrum of the red shape and each one of the interpolated spectra. As you can see, this is the result that we obtain, where the first yellow region is the union between the red shape and the first green shape. The last region is the union between the red shape and the last green shape. And all the regions localized are the linear interpolation, and they are quite smooth, but we never see those regions in the training set. So this is quite interesting that we are able to generalize to never seen interpolation. The last task that we are going to see is the shaped retrieval application. And this can be described as following. Say that we have a collection of shapes and we are given a query that is another shape, and you want to retrieve the most similar shape in the collection. So in this example, the wolf would probably be the most similar to the dog. One of the most known methods to solve this problem is shape DNA. Classically, in shape DNA, you have a collection of shapes and you have a query, which is a complete shape. And you find the most similar shape by comparing the eigenvalues. But if your query is partial, then shape DNA doesn't work. With our model, you can calculate the unions of several partial shapes, and then once we have obtained the union eigenvalues, we can apply the same method to recover the most similar shape. These are the results of the top k accuracy. We observed a phenomenon in which the eigenvalues computed by our model work better than the real eigenvalues computed at the complete shape. This is surprising, and what is happening, in our opinion, is that our eigenvalues have been predicted by a learning model that has learned to be robust to discretization perturbation, numerical error, or small non-isometric deformation, to which shape DNA standard is susceptible. One of the main limitations of our work is the missing guarantee that the predicted sequences are real eigenvalues. We encourage them to be eigenvalues with the loss term, of course, but there is no guarantee. And moreover, there is some difficulty to generalize to very different boundaries that are very out of distribution compared to what we see during training. As a further direction, it could be very interesting to explore other set operations beside the union, because those operations could lead to a new modeling paradigm based on some kind of intrinsic algebra. Thank you for your attention.